Okay, I think we can start. Hello, everyone. I would like to extend a very warm welcome to all of you, and I'm glad to see so many of you have joined today. Together with Ivan Corwin, I have the pleasure of organizing this online SPDE seminar, to which we hope that we can bring together speakers from different areas of SPDEs, reflecting the diversity of topics that we have in this field. Another aim of this series is also to provide a platform for young researchers to present their work when in-person conferences cannot take place at the moment. This is why, in addition to talks given by established researchers, we will also have a fair amount of talks given by early career researchers in this series. So today we will have two talks, a 1-hour talk followed by a 25-minute talk. Before I introduce our first speaker today, I'd like to ask everyone to stay on mute during these talks. If you have questions, you can either ask them through the chat, so I will read them out to the speaker, or after the talk so that you can unmute yourself and ask this question directly. Okay, so our first speaker today is Davar Khoshnevisan from the University of Utah. So for those of you who don't know Davar yet, so he got his PhD at UC Berkeley in 1989. After that, he spent some years at MIT and the University of Washington before he went to the University of Utah in 1993. Recently named Fellow of the AMS, Davar has made significant contributions to various areas of mathematics, for example, stochastic PDEs, fractal analysis, and multi-parameter stochastic processes. We're very happy to have you here, Davar, today, and look forward to your latest work that you will present in a talk titled Ergodicity and CLT for SPDE. So the floor is yours.
Well, thank you very much for inviting me. It's great to be virtually in New York. It would have been even better to be physically in New York, and I'm happy to be, I assume, only one of the speakers in the young person section of the speakers, because of course it couldn't be anything else. I'm pleased to present to you some recent work on ergodicity and central limit theory for stochastic PDEs. This is joint work with Chen of Emory, David Nualart of Kansas, and Fei Pu, who's here. It says University of Utah, it should now say Luxembourg. Now let's see if I can actually manage this. So my thanks to my collaborators, of course, the organizers of this seminar, and all of you for coming, also to University of Utah and for many years of support at the National Science Foundation. I'm sure I'm missing many people. If I am, I apologize. So this is a talk about a family of stochastic partial differential equations. What you see here is a heat equation, just a linear heat equation. And then what you're experiencing is an external noise term. That's the eta. And there's a feedback mechanism, which is the semi-linear term. Some people call it a nonlinear term, sigma, which depends back on the solution. So this is actually one way to describe certain types of heat motion in random environment. For reasons that we will see later, we want to start at stationarity. So let's keep things simple and say we have unit heat everywhere at time 0. So we start with unit heat and then heat flows. The semi-linear term or the nonlinear term is non-random and Lipschitz continuous. So we're not doing regularity theory for SPDEs here. This is a very standard assumption. And eta is going to be white noise in the time variable, and it may or may not be white in its space variable. So this f here is the correlation in the space variable. F could be a measure. So you might be thinking, what is f of x minus y? Well, it means the same thing that delta of t minus s does. Okay, you understand that through the way this acts on phi x, phi y through integration. It's a convolution with this measure. And if you would like to have something concrete in mind, f could be a delta function, in which case this is space-time white noise. So let me show you a simulation for what some people call the parabolic Anderson model driven by space-time white noise, or the stochastic, linear stochastic heat equation with multiplicative noise. That's when sigma here, the function sigma right here, is just sigma of u equals u. And f is the delta function, so it is white noise. And for reasons that I'll remind you of if you don't know them, tell you about, which are basic reasons of existence and so forth, dimension d has to be 1. And so what we do is we take a look at the simulate the solution at time t equals 1. As a function of x, plot the solution. So that's what I'm simulating or showing you a simulation of here. I'm kind of lying to you. So the equation is up here for simplicity, but it's not really this equation. The equation is this one here, but not really. It's actually, there's a very, very large factor in front of the eta here. So it's something like 500 times u times eta up here in the equation. And the large factor accentuates the peaks of the solution. You get what you're seeing here. So the solution at time t equals 1 looks like this. And in fact, this is really heat equation on a very large torus. It's not hard to show that as the torus gets larger, you converge to the equation on the real line, which is the case when d equals 1. The solution is never 0. It's always strictly positive. So that's a theorem. If it looks like it is 0 in these voids, it's because the peaks are sufficiently tall that in order for me to be able to fit them on this graphic, you don't really see the effect of the noise, the effect of the solution when it's very small. And this property is called intermittency. This behavior that you see, it's akin to gusts of wind. You see a lot heat density followed by a period of void or not much heat density. With Kanwoo Kim and Yimin Shao, we showed a few years ago that if you fix the time and look at the solution as a function of x, under some regularity on sigma, what you see is a large scale multifractal. I prefer not to define that. It's just sort of more or less what I did. You plot the simulation and then you go stand very far back, and what you see is a fractal, and if you go farther back, you see a different fractal. And in fact, this phenomenon happens even in space-time, something to which I'll briefly return if I have time. But basically, this is a very complex landscape, this random landscape u of t comma x, which is the solution to this SPD. And it looks like this. So what you see here is, can you see my pointer here? Carson, can you nod? Perfect. So I don't have to use the Zoom facility. What you see here on the x-axis here, that I'm trying to point to, is the x variable. On the y-axis, what you see is the t variable, time. And what you're seeing for the graphic are color-coded values of the value of the solution UTX. So when you see a darker color, that means U of TX is not very large. And as the colors get brighter, the peaks start to emerge, and perhaps the tallest peak in this picture is somewhere in this region. And I hope this is enough to convince you that this really is a very complex landscape. So today I don't want to talk about the fractal behavior or the complexity of the peaks, rather the general behavior of the peaks. But it is important to observe once again that the peaks look like shot noise. So I just want to remind you of this simulation, that they really look like, they almost look like IID samples. Now, if that's true, then you would imagine you should expect to have ergodicity in the x variable. And so that's part of what we're trying to understand is the sense in which that's true and why that's true. So more generally, we're studying the heat equation up here. In general, x is in RD, where d is bigger than or equal to 1. This notation f and m just means f is a positive definite measure. So just as a point of reference, the Fourier transform is a bijection on positive definite measures, and so it's a very nice space of correlations to consider. And we start identically at the function 1. So this is just a recap of the model. As before, sigma is non-random in Lipschitz, etc. So here's a little rigorous definition of what this really means. Of course, you're welcome to look at it, but I think it's probably just fine to think of it intuitively. There's a theorem that I'd like to start with, which is due to Robert Dallong, which says that the stochastic PDE on the top of the page has a unique solution and with good properties, provided that this spectral condition D is met. So what it really says is the spectral measure of the noise, of the spatial part of the noise, has to integrate the function 1 over 1 plus z squared. And when things are simple, for example, when sigma is a constant, this is necessary and sufficient. So that's the starting point of this work. We're going to start with equations that have well-known solutions and try to say something about what they look like. So that's the existence condition of Dallong that we will need in order to begin discussing the behavior of the solution to this SPDE. So what sorts of correlation measures do this? Well, the first and foremost, in dimension 1, if f is delta function, f hat is Lebesgue measure or 1, depending on how you want to think about Fourier transforms. And so you can easily check that in d equals 1, this integral is finite when f hat is Lebesgue measure. So that means space-time white noise leads to a well-posed solution in dimension 1. Another important family of correlations, if you want examples in mind, are objects in Wiener algebra. So these are functions that are integrable whose Fourier transforms are integrable. Fourier transform acts bijectively on the Wiener algebra, and everything in the Wiener algebra is allowed. You can also do Fourier analysis on L2. And so it's easy to check, for example, using Cauchy-Schwarz, that if you're in dimensions 1, 2, and 3, any L2 correlation function works. And finally, a fourth example, which doesn't belong to the preceding, these are the scaling variant solutions. So this is when f of x is a Riesz kernel, and this integral is finite if and only if the exponent of the Riesz kernel beta is strictly less than 2. And of course, f hat is well defined if and only if the exponent is strictly less than d, because you need to have a locally integrable function. And so what you obtain is Riesz kernels are permitted if and only if beta is strictly less than the minimum of d and 2. So these are examples of correlations to keep in mind. If you want to keep in mind one example, space-time white noise is a good one. Now, it's not hard to see that the solution is stationary for every time t. After all, at time 0, you start stationary, you're just a constant. The heat operator maps constants to constants, and the noise, if you look at the correlation of the noise, it's spatially homogeneous. So the solution is stationary. So the question that I would like to discuss is it ergodic? And so here's a theorem that guarantees that the solution is ergodic at all times t strictly bigger than 1, strictly bigger than 0. A very, very simple answer. It's ergodic if the spectral measure does not charge the origin. And if sigma is a constant, this is necessary sufficient. And in fact, if sigma is a constant, this becomes an old theorem of Maruyama about Gaussian processes. For Gaussian processes, it's just a matter of computing correlations. And this, of course, has been known for a very long time. It's an easy analytic exercise that the spectral measure does not charge 0 if and only if it has no atoms at all. In other words, if it has any atoms, it must have an atom at 0. And so in fact, that's the Maruyama theorem, is that for Gaussians, spectral measure has no atoms is equivalent to ergodicity. And so what you find is that the same condition is inherited here in the SPDE. And I'll try to explain to you, if I have time, why that really is, but that's going to have to wait. A third condition, again, this is a Fourier analytic exercise, is that this condition of not charging the origin is equivalent to the statement that asymptotically, the correlation measure is differentiable in some sense with respect to Lebesgue measure. So maybe I'll state it in a special case where the correlation measure actually is a function. Okay, so suppose f is a function, not a measure, in the sense of distributions. So it's a function. Then you can identify the measure of a big ball with the integral of the function over a ball. And so this condition actually is equivalent to the statement that the average density or the asymptotic density of f is 0, which is a very natural condition. So somehow, if the noise at different points becomes on average roughly uncorrelated, then in fact everything's ergodic. And otherwise, in the sigma equals a constant case, it's easy to see that it's not true. So that's one such result that I'd like to present to you. There are additional results that one can obtain in this general area. So I want to remind you what mixing means. Of course, mixing means different things to different people. So in this context, mixing is in the sense of ergodic theory. So if you have a random field and it's stationary, then it's mixing basically means if you take a bunch of points and a second bunch of points and then start shifting the second points away infinitely far, the corresponding values of the processes become asymptotically independent. And here's a condition for mixing is that the solution to our stochastic PD is mixing at all times other than t equals to 0 if this spectral condition holds. And so this is just something, of course, it's just some condition, but the key takeaway is if you have a spectral density at all, then because of Riemann-Lebesgue, this condition always holds. And so whenever you have a spectral density, you have a mixing SPD, mixing in the space variable, which is better than ergodic. Okay, so here's a hierarchy of conditions that I've stated. For ergodicity, this is not quite true what I've written in 1. Ergodicity is not just, this is a Dallong's condition, which means that the solution exists. Ergodicity means f hat, the spectral measure, doesn't have atoms. And 2 is that if this Fourier transform vanishes at infinity, then you in fact get mixing. And of course, these conditions imply one another. 2 implies 1. And there's a third theorem which is related to all of this, which is that if you have a little bit more, so if f is in fact a finite measure, and we're assuming it's strictly positive to rule out degeneracy, but if it's a finite measure, it's easy to see that, it's not so easy to see, but it's possible to see that if it's a finite measure, the preceding conditions hold. And in that case, you actually have a central limit theorem, which holds in total variation. So one way to state that is if you look at an ergodic average of the solution over X, that's asymptotically normal in total variation. So you subtract out its mean and divide by the square root of the rate, and that converges to some normal random variable. And it's possible to show that this normal random variable is frequently non-degenerate. I don't want to talk about that condition right now. The function g here can vary in a large class of functions. Here, I've stated it for normalized Lipschitz continuous functions, and that's what this lip refers to. Normalized means at some point, let's say 0, it vanishes, and the Lipschitz constant is 1. So that's a central limit theorem. So these are the sorts of results that I'm hoping to present to you. There are lots of variations on these. All of these conditions on this page are necessary and sufficient in the Gaussian case. There are functional central limit theorems. They don't hold in total variation, but they do hold in a more standard sense of weak convergence in a suitable space. The condition that f is finite can be dropped, but at cost. In other words, this rate will change. And finally, the condition on G being Lipschitz continuous can be extended in all sorts of directions. For example, some of you care about space-time white noise where G is the log or maybe a function of the log, and such extensions are also permissible.
Davar, can I ask a question? So these are all kind of, I guess, qualitative results about, what happens as things. Do you get any sort of quantitative control, say, on the speed of mixing or how it depends on T?
Yes, so that's a very good question, Ivan. Under some additional conditions, yes, by other methods. So actually, we've written several papers on this. They all kind of look like this. All of them actually have different techniques because they're trying to do different things. So the statement that I'm saying here actually is the statement right here. I hope you can see my cursor. This statement here, a part of the proof uses the ergodic theorem, and the ergodic theorem in general has no rate, so no deterministic rate, and so this is confounded by that fact. So there's no, at this level of generality, there's no quantitative result. But for example, if g of x equals x, or if sigma of x equals x, one of the two, then in fact we can get bounds on the total variation distance between the left-hand side and the right-hand side, and then t can go to infinity with n. By the way, that's been asked by Duchel, so it's not a question that we're just coming up with here, but it does answer such questions. If I have time, I'll say something more about that. Thank you, Ivan. I hope I answered your question reasonably well. And I noticed that there's a lot going on in chat that I'm missing. Maybe at the end I'll try to read the chat as well.
Well,
okay,
anything important, we'll bring it to your attention. We've just been responding in the.
Perfect, thank you. And so as I mentioned, there is a question by Duchel, so Duchel has central limit theorems for particle systems, but it's more or less the same thing as an SPDE, and he asks whether T can go to infinity. The answer is yes, T can go to infinity, provided that it's not so fast. So the problem is if T goes to infinity too fast, when you're averaging over a big box, you start to see those peaks that I showed you. And if you start to see those peaks that I showed you, then these averages no longer look like averages of ergodic things. So you lose the central limit theorem. So the answer is yes, T can go to infinity under some conditions where we can actually quantify this. But T, of course, can't go too fast because intermittency will prevent central limit theorems after a while. And the condition is T has to be strictly less than a suitable constant times log of n. That's actually the order on which peaks start to enter the picture. So as I said, we've written many papers on this recently, and they all look the same, and they're all different. Each paper really has a new technical innovation, but there's something in common in all of them, and I'm hoping to give you an impression of some of those things in the context of the one central limit theorem and ergodic theorem that I mentioned today. So let me see if I can try to address some of that. One topic that I raised is ergodicity and mixing. So how does one prove ergodicity and mixing? Well, there's no formula, of course, but basically what you're trying to show is a sufficiently large family of ergodic averages behave like their mean. That's what ergodicity really sort of means. I mean, formally, of course, you want to prove that the invariant measure is sigma algebra is trivial, but at the end of the day, what you want to prove is that you have a sufficiently rich family of laws of large numbers. And laws of large numbers are statements that something should be close to its expectation. So maybe it's nice to try to find ergodic theorems in L2, and that would mean that the variance should be small. So if I can manage to compute or estimate variances of certain things, then maybe I can prove ergodic theorem. So that's one hope. And I'll try to discuss, at least briefly, how one can use Poincare inequalities in Mendeleev calculus to get one's hands on variances of certain objects. Another topic that I brought up was central limit theorem and total variation. I don't have time to discuss why the following is true, but there's this beautiful theorem of Nualart and Pecati, which goes as follows. So suppose you have a random variable in the space that we have been talking about. So eta is think about space-time white noise if you want. Eta is the underlying noise of our SPDE. So it has two parameters, t and x, t for time, x for space. So suppose you have a random variable f, which is a stochastic integral against eta of some predictable random field, vtx. Then then there's a quantitative estimate on the distance between f and a standard normal distribution. I'm assuming that f has mean 1. And that's the estimate, is 2 times the variance of a certain projection of the Maillard derivative of f with against f, v. And H here is the underlying Hilbert space on which Maillard derivatives can be taken. So if you have in mind space-time white noise, eta of Tx is just space-time white noise, this H here is L2 of time cross space, L2 of R plus cross R. Okay, so that's the inner product of that L2 space. You have to estimate that variance. And the square root of the variance actually controls the total variation. Now, this is a quantitative bound. The central limit theorem that I mentioned, we're not able to actually calculate or estimate this. There's an ergodic argument that shows that nonetheless this goes to 0. And so underneath all this is the ergodic theorem in various forms. But before I get to that, let me just say one more thing about this object here. So let's calculate the expectation of this inner product. So this is an inner product. I want to take this d and put it on this side. And that's called integration by parts. So if you do that, what you get is expected value of f against the formal adjoint of d, and that's called delta, which is called the score-out integral of v. Now v is predictable, so it's known that the score-out integral of v is f, because f is this integral. And so you get expected f squared. And that's the variance because f is a stochastic integral, has mean 0. So actually the expectation of this thing that you're calculating the variance of is 1. Okay. And the common point in all of this is that I want to show that some variance, in this case, the variance of this mean 1 object, or in this case, variance of lots of averages, are all small. So I have to estimate variances. So what's a good way to estimate variances? Well, here's one way. So suppose f is in a Sobolev space, Gaussian Sobolev space D12, it means it's a nice function of the underlying noise. Then there's a very nice multi-parameter extension of the Clark-Ocon formula, which looks just like the Clark-Ocon formula of stochastic analysis, which is that f is its mean plus a stochastic integral against the noise. So that's actually called Ito's theorem. But in fact, Clark-Ocon formula tells you what the integrand is. The integrand is the optional projection of the Maillard derivative of f. Okay? This f of s is the sigma algebra generated by the noise by time s. So what I want to point out is that if you have a nice random variable, then it's up to an expectation, it is a stochastic integral. Okay? And the previous slide showed you that you have a general bound on how close a stochastic integral is to a normal in distribution in total variation. So now you have a general way to try to prove that f is close to a normal because f is always a stochastic integral. And so what about variances? Well, the variance of f, you subtract the expectation, you calculate variance of this thing here. And let's say we're space-time white noise, so I don't want to worry about covariance and reproducing kernel Hilbert spaces. So if this is space-time white noise, expected value of this thing squared is the integral of this thing, the integrand squared expectation on the outside. So now if you take the square and put it inside, you get, well, that's what I just said. That's basically Ito's isometry. But if you take the expectation, you see you have here an expected value of a conditional expectation, norm outside. If you take the norm inside, Jensen's inequality, you get an upper bound. So that's Poincaré's inequality. Okay, and so if you can control the size of the Maillard derivative of a random variable, you can actually control the variance. And this is true in general, but then L2 has to be replaced by that Hilbert space, which I've been trying to avoid telling you about. It's the correct Hilbert space on which you can do Maillard calculus associated to eta. It's called the reproducing kernel Hilbert space of eta. And as I mentioned also earlier, there is this sort of tie. So I have two series of works. One is ergodic theory, one is central limit theorems, but in fact, you use one to prove the other. So they're all sort of linked. And if I may, I would like to just say a few words about just the ergodic theory part. And so I want to present to you an abstract ergodic theorem about the underlying noise. And the bottom line is we want to say something like this underlying noise that I'm trying to point to here, for every t is ergodic in X if the correlation measure of the noise, if its spectral measure does not have atoms. The only problem with that statement is that this eta is not a process, it's a distribution. And so what do you mean by a distribution being ergodic? So this is one way to formalize that. First of all, it's easy to talk about shifts of noises. And this goes back to Wiener, but let me quickly remind you or tell you. So if you have a noise eta of Tx, that's a random distribution. If you just shift by adding y to its spatial variable, I'm going to write that as eta sub y. So that's a new noise. And it's very easy to see that this new noise has the same law as the old noise. So eta sub y has the same law as eta does in any reasonable sense as a random distribution. So you started with some maybe space-time white noise, you shifted it, and you now have a new space-time white noise for every shift y. Okay, and as I said, this is really Wiener's observation. For space-time white noise, this is Wiener's observation. It's true in the more general setting of correlation measures here. And now the random variables that we care about are all functions of the noise. So I really don't want to think about random variables as such. I want to think about random variables as functions of the noise. So if I have a random variable f, I really want to think of it as f of eta. Okay, those are the only random variables I can construct on this probability space. So the example that I have in mind, or you can have in mind if you would like, is f equals the solution to the SPDE. You give me eta, I can apply the solution map, which I'm also writing as f here. I'm sorry, I'm writing f for a lot of things. So f is the random variable, but it's also the solution map of the SPDE if you want. And of course, they're more or less the same up to identification. So the solution map to the SPDE could be one such f at a fixed time t if you want, or maybe more generally. But other things are also of this type. So you start with a random variable and you think of it as a function of the underlying noise. And now, so it's easy to see that if you start with a random variable, by shifting the noise, you sort of shift the random variable on the Wiener space. So, this is a definition. So I'll talk about real valued random variables just to have a concrete statement. So now f is not the solution map. It could be maybe a solution map evaluated at some point. So you start with a random variable f. You think of it as a mapping on the noise. You create a process f of x for every x, which is just the mapping on the noise shifted by x. Okay. And for technical reasons, I'm assuming that I start with a square integrable random variable. So now I have a stationary process because eta is stationary, eta sub x is a stationary field of distributions. F of x is a stationary random field, but it's a proper stationary random field. And so you can ask yourself, when is it ergodic? Well, okay, you need some technical stuff. And the technical stuff is you need to know a priori that this shifted f of x is actually continuous in probability. But if that is true up to that technical statement, it's ergodic if and only if the underlying correlation does not have atoms. Okay, and when f is in the first chaos, that means those are all the Gaussian random variables that you can construct. This is Maruyama's theorem. So this is actually one of the steps taken in the proof of some of these results. In all steps, ergodicity is used to prove central limit theorem. It's also used to get ergodicity, which is law of large numbers. This is one of the many steps, and I just sort of hoped to identify a few things about how one proves such a result in a simple setting. So just as a reminder, I'm going to take my noise, I'm going to shift it by x in the space direction. So that's eta of x. Now I have a random variable f. So I create a new stationary field, which is f of the shifted noise. So now I have f of x. That's a stationary process. I would like to prove that it's ergodic. So maybe the simplest thing to do is, do I just have a law of large numbers? So take a nice function g and average it along the path of f. Now, if things were ergodic, of course, this would converge to the conditional expectation of g of f at a given point, given the invariant sigma algebra. Sorry, that's actually always true. That's just the ergodic theorem. But if it were ergodic, this would be a constant. So what I would like to, or hope to prove is that if the spectral measure doesn't have any atoms, then in fact the variance of the left-hand side goes to 0, so the right-hand side must be a constant. Okay, now suppose I could do that. Then that shows that in fact the expected value of your integrand given the invariant sigma algebra is the same as just the unconditional expected value, but G ranges over a large family of functions, let's say Lipschitz continuous or C1 or bounded C1. I mean, this sort of thing can be done for many, many Gs. And so by a general result, this proves that in fact the invariant sigma algebra must be independent of f of 0. I mean, the general result is just the uniqueness of Fourier transforms, actually. So f is independent of f of 0. The invariant sigma algebra is independent of f of 0. So of course, by stationarity, it's also independent of f of x for every x. That's not quite enough. That's not ergodicity. But you can imagine that you can now improve this to a statement, an improved statement about a variance, which shows that actually not only is the invariant sigma algebra independent of individual f of x's, but actually it's independent of entire vectors of f of x's. But the invariant sigma algebra being independent of all such vectors means the invariant sigma algebra is independent of f, therefore it's independent of itself, so it's trivial. So you have ergodicity. So all you have to show is that some variance goes to 0. Okay, maybe it's not enough to prove this variance goes to 0, but that's the idea. And so let's concentrate on spacetime white noise in dimension 1. This is the object whose variance I would like to study. I can't highlight it, but here it is. I'm calling it script GN. And earlier I mentioned that Poincare inequality, which I showed you how to do it in this setting, it can be useful. So the Poincare inequality involves taking derivatives. And if you're not extremely well versed with Malyavan calculus, let me just tell you that Malyavan calculus is just calculus. It's just that the underlying measure is not Lebesgue measure. It's Gauss measure. So all the rules of calculus that you know, many of them are still true. One of which is that it's a linear operation. So it commutes with integration. The other thing that you need to know is that you have a chain rule. So I want to take the derivative of this object, Malyavan derivative of this object. That's derivative in the direction of the noise. And what I just said is that I can commute the derivative of this object. I can commute the derivative with the integral. So now I have to calculate the derivative of this object in the direction of the noise. So there's a chain rule which says that the derivative of g of f is g prime of f times the derivative of f. Okay, so that's true. The only thing that you need to be careful about slightly, just as a reminder, is that the underlying noise is a random distribution indexed by t and x, time and space. So the Malyavan derivative takes random variables in the space of that noise and spits out functions of time and space. So that's the only thing you need to remember. So when you take a Malyavan derivative, you have by default a function of space and time, which I'm calling S and Z because all the other variables have been used up. That's the only thing that you need to remember. And to be careful, this derivative is not really defined everywhere. It's a kind of Sobolev space theory. So it's sort of defined for almost every Z and almost every S. But it is an equality in the sense of functions in LP spaces. Okay. So now please remember, I want to calculate the L2 norm. L2 is in this space of the Malevin derivative. Take the square and take the expectation. That's what Poincare inequality asks me to do. So I square this. I get an n to the minus 2. And I get two integrals, dx, dy. And then I want to calculate the h norm. So I get two more integrals, which somehow, here we go. There's a time integral ds, that's r plus. And there's a space integral for r, that's dz. And then if you use the fact that G prime's bounded, so G prime goes away, you use Cauchy-Schwarz, you get this inequality. This squiggle thing means just some constant, square of the Lipschitz function of G or something like that. Lipschitz constant of G or something like that. Doesn't matter. It's just some absolute constant. The point is, this is what you have to calculate. And we want to show this is small. As n goes to infinity, this goes to 0. So there's one more observation that I would like to make, is that in general, in a setting, in a space-time setting like this, what you find is if you shift f by x, the way I mentioned earlier, and then take the Malevin derivative at times s space z, that's the same as if you didn't shift f at all and took the derivative at time s, but space z minus x. So that's one more fact, which I'll show you. I can't prove this to you, but I'll show here. But I'll show you why it's true through analogy. But why is this relevant? Because you see, you have four integrals here. But actually, I can drop this y and put a z minus y here, and I can drop this x and put a z minus x here. And in that way, you will see that one of these integrals from minus n to n can be estimated from minus infinity to infinity and just takes out this object. The other one will take out the second object. There's an integral ds, that's fine, no problem. That goes with those two. You'll end with n to the minus 2 times the whole lot of constants times one integral from minus n to n dx. And that's constant over n, which goes to 0. So why do you have this shift property of the Malevin derivative? For the kinds of processes that we sort of defined here through the shift of the noise. So this is what I wrote earlier. Why do you have that? Well, let's see why it's true for very simple random variables. The simplest random variables on the Gauss spaces are in the first chaos of the Gaussian random variables, and all Gaussian random variables can be constructed in this way. So you take a nice function phi, square integrable with respect to ds dy, and you take the Wiener integral of phi against eta. So those are the canonical Gaussian random variables. So let's see why this identity is true, at least for this. Just so we can at least believe that the identity must be true. Well, so it's easy to check that if you take this random variable and now shift eta by x, so formally this is eta, this here is eta sy ds dy. So if instead of for eta sy dx dy, you write eta sy plus x ds dy and change variables, you get this. And that's actually a true identity, this here. I can't underline it. Let me see if I can use the dreaded zoom feature here. There it is. You get this identity. Okay, so actually f of x is just a stochastic convolution. And the other fact is that the Maillé-Van derivative takes Wiener integrals and just spits out the integrand. Which I'll try to do next. So if I take the Maillé-Van derivative at Zx, that just gives me the integrand. And the variables become, well, if it's S and Z, the variables are S and Z instead of Y. So you get phi of S, Z minus X. And then you repeat for X equals 0, and you see that you get this identity. And so, of course, that means that at least in this one case where F is in the first chaos, this identity is true. That if you shift F and then take the Maillé-Van derivative, it's as if you didn't shift F, but you took the Maillé-Van derivative and shifted it. And now you put everything back together the way I attempted to show you on the previous page, and you get constant over n, maybe times something which involves the norm of F in the Gaussian Sobolev space. But the point is that goes to 0. Okay, and that's the basis for the abstract ergodic theorem. If I may go back very quickly, I think I have enough time to do this. So let me go back very quickly. So actually, while I'm trying to find this, here it is. I showed you two theorems, and they're actually sort of alluded to here. One is under nice condition on the underlying correlation, the solution to an SPD is ergodic in the space variable. So that actually follows from the abstract ergodic theorem, except that instead of real valued random variables, you write infinite dimensional random variables. But also you can get central limit theorems, because in fact, when you try to apply this fact here, so the goal is to show that the right-hand side goes to 0 for F being all sorts of ergodic averages. So you have to calculate the variance of this inner product. And it turns out that the variance of this inner product can be related to variance of ergodic averages, which again, by ergodic theorems, by the abstract ergodic theorem, would have to go to 0 in L2. And that's why the total variation distance between all sorts of ergodic averages and the standard normal will go to 0, sort of implicitly through the use of the abstract ergodic theorem. But as I mentioned and Ivan pointed out, in some cases of the SPDE, as soon as I find the SPD, I will try to show it to you. One can actually estimate this thing, not using general ideas, but using direct analysis of this variance. So here's the SPD on the top. If either sigma of x equals x, so that's what the linear stochastic heat equation or the parabolic Anderson model for space-time white noises, if that happens, then one can actually estimate the total variation distance by analytic methods. So that's true. Or if the function g here is a linear function, so g of x equals x, sigma could be general, but g is not general. Then one can also estimate the total variation distance by other methods. And again, you get a quantitative form of the central limit theorem. We really don't know how to estimate the total variation distance in general. We use this ergodic theorem argument to show that it goes to 0. So I think that's an excellent open problem which eludes us. I'd like to say one thing about why it eludes us. So actually computing estimates for these Maillé-Van derivatives, I did this here for a very simple random variable. In general, it's a little bit tricky. You have to calculate many terms. And if G or sigma are nonlinear in the statements that I mentioned, the only way we would know how to calculate them is by taking a second Maillé-Van derivative. So that means that, I mean, of course, it's the same setup as here. You take a random for every s and z, you have random variables. So now you take a second Maillard derivative. What you get is a function of 4 variables. And so instead of having 5 integrals, you get many, many, many integrals. And it just becomes very quickly intractable. So we really don't know. And we would love to know how to do this. Sorry, let me just scroll forward, maybe backward. Excellent. So we really don't know how to prove this theorem the way I've written it. In a quantitative way, we don't know how small the total variation distance between the left-hand side and the right-hand side is in general. We have devised methods that allow us to do that in some settings. And as I mentioned, an advantage of that is it's truly quantitative. So t can also go to infinity up to effects of intermittency. But of course, the big problem for me in this context is to prove a quantitative version of this theorem, which brings us to the first question of this talk. And I think this is a good place for me to end. Thank you very much.
So thank you very much for the very interesting talk. Do we have questions from the audience? So if you have questions, please just unmute yourself and ask the question.
So I have a question. Like in the case when the sigma like it's just the sigma u equals u. So like you have some chaos series expansion. Like, does it allow you to deal with the case when you start from the general initial condition?
How general an initial condition did you have in mind?
So the thing you're considering is something flat, but maybe you can like allow some growth at infinity, and you can also, for example, you can consider something like a distribution, like the Dirac delta initial condition. And in particular for Dirac delta initial condition, if you divide the solution of the stochastic heat equation by a heat kernel, it's still stationary, right?
Yeah, so I think Fei will talk about, am I right, Fei? Yeah, I think Fei will talk about that specific example where sigma of x equals x. So things will change, actually. I mean, not just the statement of the theorem, but actually you have to use other methods. We don't use a lot of chaos expansions, but I suppose you could. But the point of I think that portion of this work, at least as I understand it, is that things become quite different from this. And of course, in general, you really lose stationarity. So of course, originally what we thought was that it's a little bit like ergodic theorem and central limit theorem for finite dimensional Markov processes, where, okay, so if you start at stationarity, it's easier to prove that things have the right properties, but in general, you can get away from stationarity, or at least a little bit. And so what we're finding out here is that you really can expect big changes when you go away from stationarity. And so you can't really change one to anything you want and expect something like this is true. Of course, you can have any stationary process independent of the noise, but again, you're at stationarity. If you really go away from stationarity, as I mentioned, we have examples that show that not only the techniques fail, but also the statements fail.
But like, is it possible to divide your solution by some function? Then you will still have the
so when you start with delta function, that is exactly what you have to do to preserve stationarity. Yes. Yeah. In general, I don't know.
I see. Thanks.
Do we have further questions from the audience?
I have a question. I'm Raluca. So my question is, hi. So my question is regarding the simulation. Maybe this was something that was presented at the beginning. So I was wondering, is this the heat equation on the real line, or it's on 0, 1, or on a bounded interval? And if it's on the real line, how exactly did you simulate it? Did you simulate a very large Picard iteration approximation? And then the actual integrals from -infinity to infinity were sort of chopped at a very large level?
So this is actually a simulation on a very large torus. Actually, you can sort of see it. It's a torus of length 4,500. I don't know if you can see this here, but it's a torus of length 4,500. So we're not solving the heat equation on the real line. We're solving, this is how people, of course, in numerics do this. But then the second part of your question is, how do you actually implement this, even on a torus? We just use finite element methods. The only thing you have to be a little bit careful about, because of intermittency. So it's not true what I've written here. There's a huge constant, which I don't remember, out here in front of eta. So it's a very volatile noise. That we just wanted to highlight the strength of these noises, these peaks. So in order for you to simulate that relatively reliably, using finite elements, there's a theorem of Giungi that we use, which tells you how to make sure that the solution is stable when you choose your delta t and delta x. So in standard numerical analysis of PDEs, I think delta t has to be less than the square of delta x for heat type equations. For stochastic heat equations with respect to white noise, which is what this is, it has to be delta t has to be strictly less than half times the square of delta x. So you just have to know that in order to get stable simulations. I think we chose something like, you want it to be close to a half, otherwise it becomes expensive. So I think we chose something like a third or something like that. I don't remember exactly. This is from many years ago.
Okay.
So that's the only trick, is that you do have to be careful that, because otherwise you'll see enormous peaks because of the instability of your numerical method, and we're not interested in that, in seeing.
Okay, thank you.
Davar, just looking at this picture, you see these very heavy-tailed peaks that are appearing kind of intermittently. So the sort of central limit theorem, ergodicity stuff that you're saying, how does it exactly communicate with this type of picture? Is it really only picking up these peaks, and then it's saying that the peaks are kind of randomized suitably, or?
So that's a very good question. So you have to remember that there's a time t on which this happens. And as I mentioned, I've sort of cheated here, right? I ran it long enough to get very large peaks, but to actually get these peaks in this much space, you have to run it for a while. Locally, this thing looks like Brownian motion. If you zoom in, unfortunately, I'm not able to do that. This is just a static PDF file. But if I zoom in, say here where the cursor is, what you sort of see is locally a Brownian motion, as I know many of you know. And Brownian motion will, of course, not produce peaks like this. So what you have to do is you have to use the fact that the solution starts to decorrelate from itself and run it long enough, both in space and time. And so actually, what we're really talking about in this picture is central limit theorem when you're averaging over this part of the space, when you're not really seeing very big peaks. You're just studying typical peaks. So it still is shot noise on the right scale, but it's not these, you don't see these obscenely large peaks as functions of time. So these are like e to the constant times t. You don't see things like this. And in fact, since you sort of mentioned it, here's what I think is almost a, not quite a conjecture, but almost a conjecture, which is that in many of these problems, for example, if in this case where sigma of u equals u, we can really prove that if t, so let me turn this around. I don't know if you remember, but we integrated over some box of length n in space. So let's actually not think of n going to infinity. Let's think of t going to infinity, okay? And n is a function of t. So n can't be much larger than e to a small constant times t. And if you think of it that way, and those of you who know a lot about the stochastic heat equation will know that if you go, if x is much larger than e to the t, then you start really picking up these peaks. And so what you would expect is, you should expect shot noise. I mean, this looks like shot noise, so that's sort of like ergodic objects. But one or two peaks will completely bias the behavior of the average. And so what you should expect are stable limit laws rather than Gaussian limit laws. I have no idea how to prove that. but I think there are hierarchies on which one gets non-Gaussian limits in this business if t goes to infinity faster than the rate that we much faster than the rate that we have. But I don't know how to prove any of that. It is a nice problem.
Okay, thank you very much. Are there further questions? We can have one more quick question if there's one from the audience. Okay, if not, let's thank Davar again for this very nice lecture.
Thank
So
you.
we will have a 3 minutes or 4 minutes break before we continue with Fei's talk.